And so lauric acid is a fatty acid, right? And let's see, anybody had anatomy and physiology in here? Okay, so you know what a true fat is. It's a triglyceride. It's the triple ester of glycerol with fatty acids. Lauric acid is one of those possibilities. This is going to be the solvent. So you determine the freezing point of the solvent first with nothing in it. And then we're going to put benzoic acid in it. Is the solute. And that's going to depress the freezing point of the mixture. Okay, and we're going to use the formula, freezing point depression, change in freezing point, equals this K value, which is for the solvent. It's the freezing point depression constant for lauric acid. And we're going to multiply that times the molality. We don't need an I in here. We don't need a Van Hoff factor because neither lauric acid nor benzoic acid dissociate. So when you get molality of one, that's the molality for the equation. What we need is a value for K, which is 3.90. This K freezing point for lauric acid is 3.90 degrees C per molal, but the way they've written it is degrees C kilograms per mole. Notice molality is in the denominator. So if you make the equivalent of molality in here, which is moles per kilogram, right? Then you put it in this equation like that, it flips over. This is the denominator of the denominator, makes it the numerator. So that's why it flips it. So it's the same expression. It's the same number with different units, but the units are related. Okay. So the problem says you have 7.98 grams of lauric acid, 7.98 grams of lauric acid, and its freezing point is 43.75 degrees C. So the solvent, the freezing point of the solvent, let's do it this way. Temperature, the freezing point of the solvent is equal to 43.75 degrees. So they've got better thermometers than we do. It's probably digital. Okay, that's the solvent. We dissolve 1.03 grams of benzoic acid in that lauric acid. Now, the freezing point of the mixture has changed. It's decreased to 39.43 degrees C. Okay. Let's see. And the accepted value for the benzoic acid, let's see, molar mass of benzoic acid, accepted value is 122 grams per mole. Okay. We're going to use this information to determine the molar mass of benzoic acid. All right. So if we're going to use this formula, we also need the formula for molar mass. Molecular weight which is the way I abbreviate it, is mass per unit mole, grams per mole. Okay? So, do we have the mass of our solute? Because that's what we're after, the benzoic acid. Yeah, we do. 1.03 grams. We just need how many moles? Right? So if we use the freezing point depression, the change in freezing point, we need the difference between these two values. Right? And it's an absolute value. Right? It's not going to have any, it's not going to be negative. Boiling point would be a different story. But it's going to be, let's see, 3 has 2 and 3 and 4. 4.32 degrees C equals a change in temperature. So that's what we put up here, 4.32 degrees C. The K value is 3.90 degrees C per mole. Okay? And the molality is our unknown. Okay? I guess everybody's okay. So let's solve for this one. This would be that value divided by this value, correct? Yeah. So molality is equal to 4.32 degrees C divided by 3.90 degrees C per molal. And let's see what that would be. 4.32 divided by 3.90 is 1.108. Molal. That's moles per kilogram. Moles of solute per kilogram of solvent. 1.108 moles of solute benzoic acid per kilogram of lauric acid. Okay? All right. How are we going to find moles of benzoic acid? We just multiply it by the mass of the lauric acid, 7.98 grams. But that's kilograms, isn't it? All right, so we need kilograms of lauric acid. So how many kilograms is 7.98 grams? A kilo is 1,000. All right, so if the unit gets bigger, the number has to get smaller. We have to move 3 places this way. 1, 2, 3, here. 0.0798 kilograms. Okay. So if we multiply this times the kilogram of solvent, 0.00798 kilograms, the kilograms cancel, leaves us with moles of benzoic acid. 0.00798. So that's 8.84 times 10 to the minus 3. 8.84 times 10 to the minus 3 moles of lauric acid. Now we can finish this off. This is 1.03 grams per 8.84 times 10 to the minus 3 moles. Let's see. So let's see, 1.03, and let me flip that and then divide. So I get rounded off 117 grams per mole. Okay. Does it ask the percent error? No, just the mole mass. If we did the percent error, how would we do it? Percent error is the calculated value minus the accepted divided by the accepted times 100. So that would be 117 minus 122 divided by 122 times 100. Which will be minus 4.10. 4 point, well, let's see. Hold on a second. No, it's minus 4%. Because when you subtract these two, you've only got one significant figure left. So it's minus 4% error. That wasn't part of the question, but it's always good to stay current. Keep your skills. These are perishable skills we're developing here. If you don't use them, you lose them. Okay. Is everybody okay with that? Because that's what you're going to do with the data you get today. You're going to measure the freezing point of your lauric acid, certain mass. Then you're going to put a certain amount of benzoic acid in it and measure it again. So how do we measure the freezing point of something like this? I mean, do you stick your thermometer in the solid and watch it until it's all, and put it in the heat and watch it until it changes? It's more difficult to do it that way. What you do is melt it first, make a liquid, and then let it solidify. And that's the temperature you're looking for. All right, so you just need two temperatures. One is the pure, one is the mixture. All right, safety concerns? Hot, right? Yeah, boiling water is hot. Heat is primarily it. Benzoic acid, right? These things, they can give off some dust. Lauric acid is not a problem. Benzoic acid can be a problem with the fine particles if you breathe them in. So you just, keep your distance. It'll be all right. Huh?